Yeah.
Super target rate.
All right, how's everyone doing today? All right. Okay, so last time we were talking about how the derivative actually tells you a lot about the shape of a graph. Specifically that if your derivative is positive on some interval, that means your function is doing what there? Increasing, going up. And if the derivative is negative, it's going down. You have a take-home quiz for me? Yes, y'all can just kind of like try and get them all passed up here. So if the derivative is negative, we know that the function is decreasing. And if the derivative is constant, or sorry, is 0, then we know it's a constant function, like it's flat. Right? Yes. So I thought we'd start with an example, because we did do one, but let's do another one. Something slightly more involved, perhaps. Any issues with the mean value theorem? Homework from the mean value? Okay, so let's look at this function here.
There wasn't a video on that.
There wasn't? For the homework?
Yeah.
Oh, there wasn't? Oh, I didn't know that. Oh, okay. Yeah, were you able? You can probably check your answer in the back of the book.
It's just hard.
Because all you're doing is trying to figure out the values of C.
Well, I have it on the computer.
Okay, so there it is. So we're going to take a look at this function. F of x equals 5 times x to the 2/3 power minus 2 times x to the 5/3 power. And what we'd like to do here is find where f, and I'm going to use this little arrow next to f like this to represent increasing instead of writing the word increasing. Find where f is increasing. Find where f is decreasing. Find any local maximums or minimum values. Right? So there's 3 things that we're looking for here. Now, the big change from last class is that now we're looking at functions on their implied domains. So we're not given a domain restriction. We're not on a closed interval anymore. So let's just do a quick little check on this function. Do we have any domain restrictions here? Are there any values of x we cannot plug into the function? We're okay, right? Because this really means 2/3 means you take the cube root, right, and then you square it. And we can take the cube root of any number, positive or negative. So we don't have any issues here. And then this is also a cube root, and then we raise it to the 5th power. So we should be good as far as domain. The graph of this function should exist both to the left and the right forever. All right, so how do we figure out where the function is going up, where it's going down, and the local max and mins? How do we can do this? What do we start with? Take the derivative, okay? So let's take the derivative. The derivative of this function is, let's see, 2/3. We're doing power rule, so 10/3 x to what power? Negative 1/3, so we're subtracting 1 from 2/3. And then the next one will be negative 10/3. And then x to the positive 2/3. All right, so all we're doing is power rule here, right? Okay, so what are we going to do with that derivative? Set it to 0 and figure out if it's ever undefined, right? So keep in mind here, when we're setting the derivative equal to 0 and finding where it's undefined, we're really looking for the critical numbers. That's what they're called, right? So we're trying to find the critical numbers right now. So to find the critical numbers, we're going to set the derivative equal to 0 first. So let's go ahead and take care of that. So if I set this derivative equal to 0, I think I'm going to rewrite it a little bit first. So I'm going to rewrite this as 10 over 3 times x to the 1/3 minus 10x to the 2/3 over 3 equals 0. Okay, so I'm just trying to rewrite it so it doesn't have negative exponents, right? Dropping this down so it joins the 3 and then leaving that one on top with the 10. Is that good? Okay, so what do we do, or what have we done in the past when we have something like this? Yeah, you could clear the fractions right now. I recommend putting everything together on one side, like not together, combining getting a common denominator. Jeez. Now the danger in trying to clear the fractions right now is this: if we multiply both sides right now by 3 times x to the 1/3, it's going to go away here. The 3's will cancel, and we'll get something up over there, and then on that side we'll get something, right? 0. You might miss one of the critical numbers on the next step when we try and figure out where it's undefined. It may happen. I'll illustrate this a little more. Let's work through this first. Let's get a common denominator and see where we go. All right, so what do I need? What's my common denominator? 3x to the 1/3. So this is just missing an x to the 1/3. So I put x to the 1/3 here, and I do it on the top, right? Yeah, it's gonna make this a nice number up here when we put those together. So our new numerator is 10. Take away 10 and just x, because these two multiplied, add the exponents. 2/3 plus 1/3 is 3/3, and that's 1. So that's nice. And then we have all of that over our common denominator, which is this, and that equals 0, right? So now we have a fraction equals 0. The only time a fraction can equal 0 is if the numerator is 0. Question? Question? No? Okay. So all I have to do now is set the top equal to 0. 10 minus 10x equals 0. And solving that, you should get x equals 1. Right? So we have one solution here. That is one critical number we get when we set the derivative equal to 0. Now what we need to do is figure out where the derivative is undefined. So where is the derivative undefined, or where does it not exist? I don't care how you say it's undefined or not exist. You can say it both ways here. So how do we do that? We look at the derivative, right? And we figure out where we have problems. Now our derivative's up here, right? Right, this is it right here. We cleaned it up and then we put it together, and so this left side is our derivative, right? Right there. I think that's the easiest one to look at. If we look at that right there, is it obvious that 0 is a problem? We get division by 0 if x is 0. So we have a critical number here. X is equal to 0 will cause division by 0. So this critical number, 0, is actually in the domain of this, right? Like in the original function, 0 can be plugged in, but you can't plug 0 into the derivative or you have a problem. So two critical numbers, and now what do we do? Once we have our critical numbers, what do we do? Not yet. That's what we do on closed interval, okay? Closed interval, that's what we do. But here on open interval, it's kind of a different approach. Number line. We're going to draw a number line. Okay? So that's the big difference now, is that we're going to draw a number line. And on this number line, we are going to plot our critical numbers. Our critical numbers are 0 and 1, right? And that is going to create a very natural partition of our number line into 3 regions, right? And all we're going to do is check within each region, pick some test points, and take those test points and plug them into the derivative to see if we get a positive or negative answer out, all right? So I'm going to take 3 test points. I'm going to mark them with little X's. Anything you want over there, anything you want. -1, okay. Anything here. 1/2, okay. Anything here. 2, could I have chosen 10? Sure. Right? Okay, now these get plugged into the derivative, which I erased. Great, thanks. Good job. Okay, so I'm going to take into the derivative, I'm going to plug -1 in. Into the derivative, I'm going to plug in 1/2. And into the derivative, I'm going to plug 2. Now our derivative, I'll put it back up here and I'll rewrite it. It was 10 minus 10x over 3x to the third, right? That's it cleaned up, right? All right, all we care about is whether or not we get a positive or negative answer, right? If the answer is positive, that tells us our original function is going up. If it's negative, it's going down, right? So you can actually plug these numbers in, all right, and get a numerical answer, or you can just think through it. If I plug in -1 right here, right there, -1, that's going to become 10 plus 10, isn't it? So the top is going to be positive, and I'm dividing that by, what happens if I plug in -1 right here? What's the cube root of -1? Still -1, then times 3, it's going to be negative. I don't care about, GLC, I don't care about the actual value. I just care that I'm getting a ratio of a positive number over a negative number, and that's going to be negative. All right? So what does that tell me is happening over here? Our original function is going down, right? Our original function is decreasing over here. All right, now we have to check 1/2. So let's plug 1/2 in here. If I do 1/2 of 10, that's 5. 10 minus 5 is going to be positive. And then the denominator, if I plug in 1/2 here, the cube root of 1/2 is a positive number still, right? And then times 3, it's still positive. What's going on here? All right, so positive there. Positive over positive is positive, which means my original function here is increasing. And then when we plug in 2, on the top you get -20 times, or 10 minus 20 or something like that. So you get a negative over there, right? Okay, and that means my function is going down. And I always have students ask me, will it always switch? You know, do you have to check them all, or can you just find the first one and then just know that they switch every time? And the answer is you have to check them, all right? Because some functions they switch, some functions they don't, all right? Okay, now from this we can start answering the questions. Let's first talk about where this function is increasing. F is increasing where?
0, 1, 0.
Only between 0 and 1, right? Between 0 and 1. So right in between here and here, right? Between here and here, this is where our function is going up. So I need to put the answer as an interval in terms of the x variable. So it's all values between 0 and 1, correct? Now the question becomes, do you include the endpoints or not? Do you include 0 and do you include 1? And let me just give you the basic answer. Just don't include them, all right? Even though we can plug 0 into the function, can't we? And we can plug 1 into the function. That's allowed? To talk about a function increasing means you have to have at least 2 points. So you can't ever talk about whether or not a function is going up or down at a single point, 0. So we don't lose anything by not including that single point. And it's safer to do this because there are some times that we'll run into a problem where one of these endpoints is not, one of these critical numbers here is actually not allowed in the function. And so if you put a closed, you're gonna be wrong because that number's not in the domain. So just always leave them open. It's easier that way. Understand? Okay, next we want to know where it's decreasing. So that's everything over here, right? All the way that way, and everything over here all the way that way. So that's 2 intervals. That one's got to have negative infinity in it, and this one's got to have positive infinity in it. So how do we do that again? How do we group 2 different intervals together? Union. So we're going to go negative infinity all the way up to where? 0, right? And then we union that with from 1 on, right? Who said 2?
I said 2.
Okay, so I'm glad you said 2. That's one of the most common mistakes I see is people will accidentally grab the test point, right? That's why I circle my test points. I'm trying to distinguish them from my actual critical numbers, all right? And I also put X's here because later on we're going to be graphing, and I don't want to put dots there because you might confuse dots as part of the graph. So there's reasons why I'm using X's and circling my test points. All right. We've answered 2 of the 3 things. Now we want to find if this thing has any local maxes or local mins. So let's talk about local max first. Do we have any local maximums? What's that? What are we looking for? What tells us we have a local maximum? If we ever go up and then back down, right? If we go up and down, we have a local maximum. So we're going up here and we're going down here. Now we do have to check, is our function defined at 1? Yes, it is. Okay, so we don't have anything. Let me show you a function real quick. What if we had a function that did this? Had a vertical asymptote like this, and then like this. Okay, look at that function. Do you agree that to the left of this point we're increasing? Do you agree that to the right of this point we're decreasing? And our table would have shown us that. It would have said we're increasing and decreasing. But do we have a maximum there? No, and the reason is because at that point our function is undefined. So you always want to be checking for the up and the down, which we have, but you also want to check that this number is actually in the domain, which it is. So we can be assured that this is where we get a maximum. So we have a local max at f of 1. So what I'm doing now is I'm going to take that value 1 and I'm going to plug it into the original function, and that will give me the actual value that comes out. So when you plug 1 in here, that's pretty easy to plug in, right? You should just get 3, right? 3. So the actual local maximum value is 3, but it happens at an x value of 1. Questions? How about local min? We're looking for, what are we looking for with local min? Down then up, right? Down then up. It happens at 0. And again, 0 is in the domain of the original function, so there should be a point there, no asymptotes. So f of 0 equals 0. Now, are we saying that the highest point on this graph is 3? Are we saying that the lowest point on the entire graph is 0? No, we're saying locally we're going to see like a hill and a valley, right? A hill and a valley. Let's graph it. 5x to the 2/3. I wonder how this is going to handle these rational exponents. Minus 2x to the 5/3. There it is. Interesting looking graph. Would you all agree? Interesting looking graph. We were able to identify the point 1, 3 and the point 0, 0. Those are local maxes and mins. Y'all see that? 0, 0 and 1, 3. Al, question? No?
I noticed that at 0, 0, the derivative is not defined.
That's right. Right, and remember when we were getting our critical numbers, what were the two things we were looking for? Where the derivative is 0 and where the derivative is not defined. And we said that at 0 we should have an undefined derivative. And that's exactly what happens. We have an undefined derivative there because we have a cusp. Yeah. Okay? So it's actually kind of amazing that by just taking the derivative and analyzing those two things, you can say a lot about this function. You can tell where it's going down, where it's going up, right? Like to the left of 0, our graph's going down. Between 0 and 1, our graph's going up. To the right of 1, our graph's going down. We knew all that, right, without the graph. Yeah. All right, let's do one more. trying to get you a nasty function here, something nasty. So I'm going to give you one. I actually put this one on a test, and I think the wheels completely came off for most of the students. But it came straight out of the book. It wasn't a homework problem, but it was a problem from the section. And yeah, it didn't go well. That's what I remember about it, but let's just take a look at it. Function is 1 plus 1 over x plus 1 over x squared. Yep. Oh, no, that's a minus here. Sorry. Minus right there. Yeah. Okay, let's talk a little bit about this. Do we have any domain problems? We do at 0, right? So let's keep that in mind here. For this, x cannot be 0. When we're talking about domain, right? The x cannot be 0. Let's just keep that in mind as we move through this problem. All right, so we're going to go ahead, same 3 questions. Where is it going up? Where is it going down? Max and mins, right? So let's take our derivative. All right, the derivative of 1 is easy, right? What about these two? I would recommend maybe you rewrite this problem. So bring that x up, bring the x squared up, and that way you can use your power rule to take the derivative, right? That would probably be the most efficient way to do it. So taking derivative of this is the same as taking derivative of this, which would be what? Negative x to the negative 2, and then plus 2x to the negative 3. So we're just bringing those powers down, subtracting 1 from the powers, and there's our derivative, right? Now we want critical numbers. These are the numbers that'll go on our number line. Okay, so we're going to set this derivative equal to 0. Let me rewrite the derivative first. I'm going to rewrite the derivative as negative 1 over x squared plus 2 over x cubed. Right? That's just maybe a little bit easier to look at. Right? That is what it is. Now let's set it to 0. Okay, when I do that, I'm going to need a common denominator, right? So I'll have to multiply the first term by x and x, right, on top and bottom. So we should get negative x plus 2 over x cubed. Set that to 0. And the only time that can be 0 is if the top is 0, right? So we should just get a solution of x is equal to 2. We go with that? X is 2. Now, this is the part that's a little weird. Where does the derivative not exist? At 0, right? Okay, so this is where it gets a little confusing, because can we say that 0 is a critical number? No, because 0 is not in the domain of the original function. So technically, even though this is a critical number in terms of looking at the derivative, it's not a critical number because that number is not allowed in the domain. But here's what makes it even more confusing. We're still going to put it on the number line. We're still going to put it on the number line because something at 0 might change dramatically with the function because of this. So it's not technically a critical number, but it's still going on the number line, all right? So I'm going to put here like it's not, but it kind of is, all right? If you look back at the definition of critical numbers, which was a while back, it was any point C within the domain of the function f such that the derivative doesn't exist or the derivative is 0. But it was implied in the definition of critical number that it had to be in the domain. So, all right. We ready? Number line? Here we go. So number line I'm putting 0, and I'm putting 2. And now I pick 3 test points. One here, one here, one here. So I'll pick -1, I'll pick 1, and I'll pick 3. Those seem natural, don't they? And where are those numbers going? Into our derivative. So I need to figure out what's f prime of -1, what's f prime of 1, what's f prime of 3. Those 3 things we need to determine. And I conveniently left our derivative right here, the one that we cleaned up. That was it right there. I left it there so that we could use it. Questions? Do I need to slow down? You all doing all right? What happens when you plug -1 in? On top you get positive, and on the bottom you get -1 cubed is negative. So you should get negative here, and that means over here our function is going down. All right, what about at 1? So at 1, we get -1 plus, so that's positive on top and positive on the bottom, right? So we get positive over positive, which means positive, which means now our function is going up. And then at 3, what do we get? Negative. Negative on top and positive on the bottom, so we should get a negative here. So now our function is going down. All right. So let's talk about where our function's going up, then where it's going down, then we'll talk about our local max and mins. So this function is increasing where? Between 0 and 2, right? Between 0 and 2. So I'm just going to put 0, 2. Now, having, again, the parentheses is the safe way to go, and it's not incorrect. But let's say you wanted to be, like, you wanted to actually include some endpoints. Could you put brackets on both the 0 and the 2? You couldn't. You can only put it where? Only on the 2, because the 0 is not even the domain of the original function. That's what I was trying to say earlier. That's why it's safer to just do parentheses. All right, where's our function going down? -infinity all the way up to 0, union with 2 to infinity. Local max. We're looking for our function to go up and then down, right? Our function here goes up and it goes down, and 2 is in the domain of the function, right? So let's go ahead and evaluate our function at 2, our original function at 2, see what we get. That's not very pretty, but it's 1 plus a half minus a fourth. 1 plus a half minus a fourth. So what is that? Is that 5/4? 5/4. So at 2, we get a value of 5/4. That should be a local little hill we see, right? Then we have to talk about local minimum. What's that? None? Well, wait a minute. I thought we're going down then up. Yeah, but 0 is not in the domain. 0 is not in the domain. So you can't have a local minimum here. In fact, if you tried to figure out what it was, what would happen? You plug 0 in, right? And you go and you get division by 0. So you should know there's a problem, right? So for local min, you just say none. All right?
So for critical numbers, you also want to include it in the sign domain?
Say again?
For critical numbers,
Uh-huh.
you always want to include it in the number line in the sign domain?
Critical numbers always go on the number line. But also you put on the number line any points where your function is undefined. All right? Because you need to look at what's happening there. Let's take a look at this function. 1 plus 1 over x minus 1 over x squared. There it is. I'll move it over. So we found a local max at 2, right? I'll zoom in a little bit. Hard to see that, but that point right there is our local maximum. It is the highest point locally. It's a little hilltop here. See, it's kind of difficult to see. You have to trust the math. Don't trust the picture, trust the math. The math will confirm that that is the highest point. So if you go any point near that, you should be higher at that middle point. And then at 0, obviously, we have some crazy stuff happening. We have an asymptote. It just goes off, takes off to negative infinity on both sides. But it's not a local min, right? Okay, what do you think? What's that look, Jane?
Yeah.
Yeah? Okay. All right, so summary. First derivative tells us everything we need to know about where a function is going up, where a function is going down, and from that we should be able to determine any local minimums and local maximums of our function. So long as we can take the derivative, so long as we can set it equal to 0 and figure out where it's undefined, we're in business. Agree? So that's what the first derivative tells us. What does the second derivative tell us? Because the second derivative also tells us something about the function's shape. And it's not as obvious because we haven't really talked too much about the second derivative and how it relates to the shape. So here, this is it, all right? Right there. Okay, I'll put it right there. So you know how if the first derivative is positive, our function is going up? First derivative is negative, our function is going down. If you look at the second derivative and figure out where it's positive and where it's negative, it tells you about something called concavity, the concavity of the function. And it's not complicated. It sounds complicated, but it's not. So let me show you a picture first. Take a look at this, and I'm going to start moving this around. Now, the slope of the tangent line here, the first derivative right now is what? Positive or negative? First derivative is positive. We are increasing, right? But the second derivative right here is negative, and I'm not explaining why yet. And then it's going to, see it's red? Okay, so still our second derivative is negative until we get right there, and then something happened. Something happened right here at this point. We went from a negative second derivative to a positive second derivative. And then when we get there, it changes to a negative second derivative, and then right here changes to a positive, and it remains positive the rest of the way. So can you tell from those pictures what it is, what concavity is really telling you about the function? Negative concavity, positive concavity, negative concavity, positive concavity.
Is it like telling you the way it bends?
The way it bends, yes. It's like a smile or a frown. That's what it all, the second derivative is all about smiles and frowns, okay? See this graph right here? The part that's red, that's all part of a frown, isn't it? Like, someone's mad, right? Sad or mad, yes? But then this part of the function right here looks like just like one half of somebody's smile, yes? And then part of someone's frown, and then part of someone's smile, yes? But it does not have anything to do with increasing and decreasing, right? It's that shape, whether it's curved down, concave down, or if it's concave up. Make sense or no? Okay? So let's do, what is this? I don't remember. Okay, so there, right there, that point right there is where we have a switch, a change in our concavity. It's where the frown meets the smile, right? The two come together right there at that point. And so to the left of that point, we have the frown, which means the second derivative is negative. And that's pretty easy to remember because like people who are negative, they like to frown a lot, right? So second derivative, negative people frown, right? But then right at this point, they become happy, smile, right? Positive people smile, concave up, yes? That point right there has a special name. the point at which it switches from a frown to a smile is called the inflection point of the curve. All right? Now, we have more than one inflection point here. We have a second inflection point. There it is right there. That's where we're going from the smile to the frown, right? And then we have a third inflection point right here where we're going from the frown back to the smile. Okay? What's that look today? You okay?
Yeah.
All right. All right, so coming back up here, the summary here is if the second derivative is positive on an interval, then f is concave up there. If the second derivative is negative on an interval, then it's concave down on that interval. Any point on the curve where you get a change in concavity, either from positive to negative or negative to positive, either way, if there's a change, then you have an inflection point there. Okay. You all good? All right, so what I'd like to do now is I'd like to look at the problem we just did. I've already asked you to tell me where this function is going up and where it's going down. I've already asked you to find any local maximums and minimums, which we've done. Now I'd like us to take a look at this, and I'd like for us to talk about the concavity. Where is this graph concave up? Where is it concave down? And where are any inflection points? Right? So those are the three new questions. Find where f, and this is the way I'm going to say concave up, and draw a little smile next to it. Find where f is concave down. And finally, find not local max and mins, just inflections. Three new questions, right? Three new questions. How do you think we're going to do it? We're going to do the second derivative. We're going to set it equal to 0. We're going to figure out where the second derivative is undefined. We're going to draw a number line. We're going to do test points. And the test points will tell us whether or not our second derivative is positive or negative, and that'll tell us about frowns and smiles. So it's basically a complete repeat of everything we just did, but working with the second derivative instead of the first derivative. That's nice, right? Okay. I'd say the one main difference, well, there's a couple of main differences, but the second derivative is not going to tell us about up and down. It's only telling us about frowns and smiles. And then also, anywhere where we see a switch, right? You know, with the first derivative, we were looking for up and down for maxes, and we were looking for downs and up. We don't have those two different categories now with the second derivative. We just have anywhere it changes, we have an inflection point. All right? All right, so we need the second derivative. Now, we had taken the first derivative, and we had cleaned it up, and I have promptly forgotten it now. So what was that first derivative? It was negative x plus 2 over x cubed. Okay, that was it right there. So we need to now take the derivative of that. And so, I don't know, do y'all want to work with that, or do y'all want to go back to the other version? Because we had another version of it. So we have that versus negative 1 over, no, it was before that. Negative x and negative 2? Is that what we had? Plus 2x to negative 3, right? Remember that version? So which one would you rather take the derivative of? I don't care. I think they're both equally. I mean, this one's just power rule, right? Drawback to this one is after we do it, we're still going to have to like rewrite it and get it to look nice. This one, quotient rule. So it's your choice. The good news is you're going to get the same result. Okay, that's the great thing about math. Okay, is that as long as we do it right, we should all get the same result. By the way, I got that thing to work, but I had a little bit of problem with the printing it like a pyramid, but I did get it to spit out. Yeah, but we can talk about it later. I don't know if I'll have time after class, but okay. What do y'all want? Left or right? Right. Okay, so let's do a derivative of this one. So the second derivative of this function is, okay, negative 2 comes out, so we're going to get positive 2x to the negative 3, and then we're going to get negative 6x to the negative 4. There it is. And now we get to clean that up, because we have to set it to 0 and figure out where it's undefined. So this is 2 over x cubed minus 6 over x to the 4th, which turns out to be 2x minus 6 over x to the 4th. That's just me multiplying top and bottom here by x. And there it is. That's actually not too bad looking, is it? Not too bad? Would you agree? Just for the sake of doing it. If you did quotient rule, here's what you should have got. Negative 1, derivative of the top times the bottom, minus derivative of the bottom times the top, all over the bottom squared. And then what you'd have to do is clean up the top. So you'd have negative x cubed here, and then we distribute there, you get plus 3x cubed minus 6x and squared. And then you could put those together. I'm just working on the top here. Put those two together so you get 2x cubed minus 6x squared on top. Factor an x squared out, reduce it out with this. That becomes x to the 4th. That becomes 2x minus 6. So you get the same thing. All right, now we want to know two things. These are like critical numbers again, right? We want to know where's the second derivative equal to 0. Let's do that one first. So where's the second derivative equal to 0? At x is 3. You just set the top to 0 again, right? So x is 3. And then where does the second derivative not exist? X equals 0, right? However, that's not in our domain, right? It's not in our domain, so we don't really consider that. We draw a number line. What goes on our number line? 0 and 3. We pick test points, negative 1. Let's go with 2 and 4. And where are those points getting plugged in? To the second derivative, because second derivative tells us about frowns and smiles, right? So we want to plug this into the second derivative. So we need the second derivative at negative 1. We need the second derivative at 2. And we need the second derivative at 4. All right, here's our second derivative right here. There's something really nice about this second derivative. The denominator is always positive, right? Because it's to the 4th power. So no matter what we ever plug in, the bottom is positive. So really, it's just all about the numerator. Whatever the numerator turns out to be is what it's going to be. So when we plug in negative 1, what do you get? 2 times negative 1, negative 2 minus 6. It's negative, right? So since we get a negative number here, what does that tell me about the picture of f? What does f look like over here? It's frowning. Negative is frown, right?
Yes.
Unhappy people. Unhappy people frown. So my original function looks like this over here. All right, what about at 2? Plug 2 in. Still negative, isn't it? Still negative. My original function here is frowning still, not happy. And then when we get to 4, plug 4 into that, the top becomes 8 minus 6 is 2. It's positive now. So now we're concave up. Make sense? So we should now be able to answer the questions. First question was, where is this function concave up? So where is this function concave up? From 3 on, right? 3 to infinity. Okay, where is our function concave down? This one's a little tricky. Where is our function concave down? Negative infinity to 3 or to 0? You have to go to 0 and then union and go from 0 back to 3. Because here's the problem. It is concave down all the way through here, but 0 is not in the domain. So if you say it's from negative infinity to 3, then you're saying 0 is in there too, right? But it's not even defined. Your function's not defined at 0. So you have to work your way all the way up to 0, union that with from 0 on. And the fact that these are parentheses means like we're jumping over 0. Make sense?
If 0 was in domain, it would be negative infinity to 3.
Yep, if 0 was in the domain, then you would just go from negative infinity to 3. All right, how about inflection points? Do we have any inflection points? Okay, anywhere where we see a change in concavity, right? Anywhere we go from smile to frown or frown to smile, which happens where? At 3, right? Now we also have to check, is 3 in the domain? It is, right? What if we had a change in concavity at 0? What if it was like smile here, frown here? Would that be an inflection point? No, because you still have to be part of the domain. So that we would not consider. So basically 0 is never going to be considered, all right? Or the point that's not in the domain. But we do have an inflection point that happens. Now a lot of times with inflection points we just list the x value, like x equals 3. But we're so used to doing this anyway. Let's just go ahead and plug 3 into the function. If we do that, we get 1 plus a third minus a ninth, which is going to be 9, I think it's 11 ninths. So this 11 ninths really doesn't mean a lot to us because it's not a max or min, right? It's not a highest or lowest peak or valley. It's just, this is just where we go from a frown to a smile, right? Just at that point. So let me bring that graph back up. Let's take a look at it again. And we should see all of this within the graph. Unless I deleted it. I don't think I deleted it, did I? That is the graph, right? Wow, this is really kind of hard to see, which is why we have to trust the calculus. So where, I'm kind of erasing it. Oops. All right, to the left of 0, we should look like a frown. Here's 0. To the left of it, my graph looks like a frown. Do you all agree? Now it keeps going over here and it keeps frowning, right? It's never going to turn up to a smile. So this is my frown. Then I'm going to just get past 0 because it's not my domain. And then from 0 to 3, I should look like a frown. So if you go like this and you get to 3, 3 is right here. So I should look like a frown over here. And then to the right of 3, I'm supposed to look like what? A smile. Now that's hard to see. It's hard to see that that's a smile. But it is. There is a change in concavity there. Now let me see if I can do any sort of zooming. Yeah, I might be able to do it if I zoom in enough. Yeah, I don't know if that helps. Here's the point right here. That's the point where we have it, where it goes from a smile to a frown. What do y'all think? Can you buy it? Got to trust it. Zoom out. You want me to try and zoom out? It's just going to be harder to see. I think it's going to be harder to see. It's going to start looking like a straight line, kind of. Yeah, well, still. It's right here, right? Is this point right here? Somewhere in there? You can kind of see that it's, well, the math says it is, so. Now, I've kind of defined concavity like concave up and concave down. The way I've kind of defined it for you is with smiles and frowns, which is kind of childish, don't you think? Yes?
It works.
There is another definition of concavity that's more precise, and I'll just explain it to you real quick. What makes a function concave down is the fact that, well, let me draw you something and see if anyone in this class can figure out the difference between concave down and concave up. It's usually really hard for students to see this. Okay, that is a concave down function. And this is a concave up function. Can you all see, like, another way other than saying smile and frown, what the difference is between these two curves?
The derivative starts positive and then goes negative.
The derivative goes positive and then negative. But if I didn't have that side, it would still be concave down, right? Like if I was just looking at that, that would still be concave down. Like I don't need the other side to say it's concave down. So I don't need the complete frown. I just need a piece of the frown. Over here, same thing. Like I can just get rid of all that. That's still concave up. So like, what is it? Go ahead.
Does it have to do with like a positive and negative secant line?
It has to do with the tangent line. Something about it.
Is it that the tangent gets closer to 0?
No, because we don't have to have it flatten out.
But it gets closer, it approaches 0.
Doesn't have to.
No.
Nope.
Is it,
It has to do with the position of the tangent line relative to the curve.
wouldn't the evolution like the next
Yeah, but if I draw you this curve right there, that has those tangent lines would be negative, right? We'll take another second on this. No?
It's not something to do with like approaching the next or moving sort of deal, right?
No, it's just something about that picture that distinguishes them.
Would it,
On the right or the left side?
What?
Either on the left or the right
What
side
side
of
of
the
it?
curve.
What is?
The tangent line.
That's close, but not quite the wording.
Is it undefined?
Okay.
is it the second derivative, like if it I guess, or is maybe that's what we just went over. I don't know. Like I feel like it would go, if it goes through it, then it means that it's concave. But if it doesn't, then if that makes sense.
Goes through it. I'm not following.
Is the space of the tangent line between the curve and the tangent line changes as you continue out?
No.
No?
Okay, look at this concave down, right? If I draw a tangent line, let me get my red here. Let's just zoom in on that one point, that one part, okay? So the purple part here, we're saying is concave down, right? And if I pick a point on that and draw the tangent line, all the points on the tangent line are above the points on the curve. So like if you go and you pick an x value, right? Pick that x value. Go up to the curve, you're going to be here, right? Where's the tangent line relative to that? Above it, right? But if you go to a concave up function, it's backwards. So if I pick an x value, let's pick this one, and you go up to the curve, here it is. Where's the point on the tangent line? Below it. Okay? So a more precise definition of the second derivative thing, concavity, is that to say a function is concave down means the tangent line is always above the curve. To say it's concave up is to say that the tangent line is below the curve. Smiles and frowns a little easier to deal with. So we'll just do smiles and frowns, yes? Okay.
You say that again, because concave down, tangent line.
Concave down, your tangent lines are always above the curve. And if it's concave up, your tangent lines are below the curve. Okay. Inflection points. Like, what's the use of an inflection point, right? Like, does it seem like local max and min, it seems like you might want to know that, right? You might want to know that, local max and min. But what's the use of ever knowing the inflection point, right? So I'm going to give you an example here. I'm going to show you this. This is just to convince you that inflection point is something that some people are interested in. So let's say I own a business, and let's say this is time, and let's say this right here is profit. Money coming in, right? Well, revenue and profit are different, but let's just say that's profit. All right, let's say I have a function that looks like this. Hold on. How do I want this to be? Yeah, let's say this. Okay, let's say my profit function looks like that. So if I'm looking at that, I'm sitting with my colleagues, right? And we're talking about our business. We're like, okay, look, obviously our profit is increasing, right? As time has gone on, my profit has increased, or our profit has increased, and it's still increasing, isn't it? It's still increasing. But something's happening right here. Right in here, we go from a smile, right, to a frown. And that point right there is the inflection point. And in terms of money, what this is saying is, look, over here, the slope of the tangent line was basically like the rate at which money was coming in. And look at how steep it is, right? Very steep, very steep, very steep, really steep. And then we got to this point, right? We hired, who did we hire? Al? We hired Al. That was it. That was that day we hired Al. And then look what happened. We're still making money, but what's happening to the slope of that tangent line? It's slowing down, right? We're still making money, but not as fast. Okay? This right here is called the point, anyone know what it's called? Of diminishing returns. Or return, whatever you want to say. Basically, it's the point at which you're still increasing, but that was kind of the best it ever got. So, we need to get rid of Al. Because apparently Al has done something to the morale of our employees. People aren't working as hard. No. You get that though? I mean, that would be an interesting point on a graph to say, like, hey, what happened here, We switched over to that new computer or something. We're using that different machinery, and so you can identify places that might be impacting your business in a bad way, right? All right, how are we doing here? 40 minutes. Let's go for one that just looks real bad. Should we go with the last problem? Well, I don't know if this is the hardest one, but it's the last problem. Usually those are the hardest, right? Let's try this one first. Maybe if we have time, if we can knock this one out in time, we maybe go after the other one. So as a self-proclaimed math dork, okay, this colleague of mine, back when I first started teaching here, the two of us, we were out in the little portable buildings. That's where our offices were. And we'd sit there and talk and stuff. And I'm not quite sure this is related to what we're doing right now, but I think it kind of is. He was telling me that he had told his girlfriend that his love for her, if he could graph his love, that the first derivative of that function was always positive. Okay? I know that sounds just so, like only math dorks would be talking like this, right? So, y'all understand what he's saying? He told his girlfriend that if his love was a function that could be graphed, if this is time, that the derivative of that function is always positive.